Hi, this is Tzvi Rosen with another lecture in our matrix theory course. Today we'll be talking about some subspaces that we associate to a matrix. Okay, let's start off by talking about the row space, column space, and null space. So we're going to fix a matrix A, so let A be an m by n matrix. Okay, then the row space of A is the subspace of Rn spanned by the rows of A. The column space of A is the subspace not of Rn, but of Rm, because that's the appropriate size of the columns, and this is the subspace spanned by the columns of A. And then the null space, it's a bit more complicated. This is the null space of A is the subspace of Rn. Okay, so this is the, if we're thinking about A as, we can think about this as a linear function from Rn to Rm. Okay, so the null space is the subspace of our inputs, Rn, which are solutions to the equation Ax equals 0. Okay, where we're looking for solutions of the form x. Okay, so vectors you can stick into this matrix, which give you back the 0 vector. Okay, so another way to think about these things, at least the last two, the column space is the image of the function. Okay, or also the range. Okay, these are the values that are output by this matrix considered as a function. Whereas the null space is the, sometimes we call this the kernel of the function. These are the things that map to 0. Okay. So let's look at a specific example of a matrix. So we'll start by computing the row space. So if this is our A, the row space will be spanned by the vectors (1, 2, 3, 0), 1, 0, minus 1, minus 2, and 0, 1, 0, 1. Okay, a valid question is this a basis for the row space? And you can check for yourselves that this is in fact a basis. This is a basis. Okay, since we know we're defining the row space as the span of these vectors, so we know it's spanning, so we just have to check linear independence. Which you can do using reducing to row echelon form. Okay. Meanwhile, if we want to know what the column space is, okay, so this will be the span of the columns. (1, 1, 0), 2, 0, 1. 3, minus 1, 0, 0, minus 2, 1. Okay, so we have 4 columns, 4 vectors here. We know that this is supposed to be a subspace of R3, so right away we know this is not going to be linearly independent. Okay, so 4 vectors in R3, that's too many. Implies linearly dependent. Okay, so what we can do is a little bit of, depending how we put it, row reduction or column reduction, we can see which vectors are in spans of the others. So we'll start off with, because we're more comfortable with row reduction, I'll put it in that way. So this will look like the transpose of our original matrix. 2, 0, 1, 3, minus 1, 0, 0, minus 2, 1. Okay, so we're going to row reduce by adding minus 2 of the first row to the second row, minus 3 of the first row to the third row. Okay, and what we get is 1, 1, 0, 0, minus 2, 1, 0, minus 4, 0, and 0, minus 2, 1. Okay, so this vector is going to be useful for us. We can multiply this by minus 1 over 4. Okay, now this matrix remains largely the same. Okay, except we're going to change this to 1. Okay, and now you can see that this 1 can cancel the vectors, the other vectors in this column with no consequence. So it's clear that we have the 1, 0, 0, 0, 1, 0 here. So this is our E1, this is our E2, and this is our E3. So that tells us that the column space is equal to the full R3, which means that every vector in R3 is in the column, is in the span of the columns of our matrix. Okay, so that's the row space and the column space. The only thing left to do is the null space. So we'll check for solutions of AX equals 0. Okay. So to find the null space, we're going to do some row reduction. So we'll copy down our matrix. Okay, we'll start by clearing the first column. We'll take minus row 1 plus row 2. That gives us 1, 2, 3, 0. 0 minus 2 minus 4 minus 2. And 0, 1, 0, 1. We'll swap these columns, these rows, I'm sorry. Okay. So we have 1, 2, 3, 0, 0, 1, 0, 1, 0, minus 2, minus 4, minus 2. Okay, now to clear the rest of the second column, we take minus 2 row 2 plus row 1 over here, and 2 row 2 plus row 3 over here. And we get 1, 0, 3, minus 2. And 0, 1, 0, 1, and 0, 0, minus 4, 0. Okay. And then we can multiply this by minus 1 over 4 here. Let me copy this. Which gives us the value 1 over here. And then we can add minus 3 times row 3 to row 1 to obtain 1, 0, 0, minus 2, 0, 1, 0, 1, 0, 0, 1, 0. Okay, now we'll justify this later, but the null space of this matrix, this new matrix we've obtained, is exactly the same as the null space of the original matrix. Okay, so null space is same for reduced and original matrix. So what is the null space of this matrix? Well, let's look at which vectors give us 0. Okay, so how do we find the null space for this matrix? What we'll find is free variables correspond to null space vectors. Okay, so in this case, we have 3 pivot variables. So these are our pivots. So those do not correspond to null space vectors, but we have this, which corresponds to a free variable. So that's going to be a null space vector. And the way we get it, we just set we set a vector, we set the coordinate to be 1 in the 4th coordinate. Okay, and then we use the equations defined by the pivots to get the values for the pivots. So I know that if the last coordinate is 1, I'm going to need the first coordinate to be 2, so that when I multiply the first row by this vector, I get 0. Again, if the last coordinate is 1, I'm going to need the second coordinate to be minus 1. And if the last coordinate is 1, I need the third coordinate to be 0. So this is the unique vector in the null space. So the span of this one vector equals our null space. Okay, and if you stick it back into the original matrix, you can see for yourself that the result is 0. Okay. Now let's explicitly state the relationship between the column space and the equation AX equals B. So the vector B is in the column space of A. This is if and only if AX equals B has a solution. Okay? So the question of determining whether something is in the column space is equivalent to determining if a certain matrix equation has a solution. Okay, so let's show how this is the case. So we have this matrix equation AX equals B, and I'm going to claim that this is equivalent to determining if 3 minus 1, 3 is in the column space of A. Okay? So the way we'll determine this is by using the augmented matrix. So we can take 1, 1, minus 1, 2, 0, 1, 3, minus 1, 3. Okay, and this goes to, so we'll use row operations. We'll add minus row 1 to row 2, and positive row 1 to row 3, which gives us 1, 2, 3, 0, minus 2, and minus 4. And then this is 0, 3, and 6. Okay, I'm going to multiply this by -1/2, and I obtain 1, 2, 3, 0, 1, 2, and 0, 3, 6. Okay. When I multiply, I can clear the first column. Let me just move stuff over a tad. I can clear the first column, the second column by adding -2 row 2 to row 1, and -3 row 2 to row 3. Okay, and what I obtain is 1, 0, -4 plus 3 is -1, 0, 1, 2, and 0, 0, 0. Okay, so we can see from this that this system of equations, this matrix equation, is consistent, and it has the solution x1 equals -1 and x2 equals 2. Okay, but I can also use this to express our vector b as a combination of columns of A. So this also means that 3 minus 1, 3 is equal to -1 times the first column plus 2 times the second column. Okay? So finding the solution of this equation is equivalent to expressing our vector b as a linear combination of columns of A. That's an illustration of how those two things are equivalent. Okay, now let's discuss how the null space of the matrix A is related to the solutions of AX equals B. So here, okay, we're going to suppose that U is a solution to AX equals B. So we're not wondering right now if it's a consistent system. We know that it's a consistent system. It has a solution. So we're going to write, so the following is true. Every solution to AX equals B can be written as U plus some vector Y. No, let's make it V, where V is in the null space. Okay. So why should this be true? Well, if I have AX, let me just write Y. If I have AX equals B, we're using U, if AU equals B, and let's say AX equals B, then using linearity, this means that A times X minus U is equal to B minus B, which is 0, which means that X minus U is a vector that maps to 0 under the matrix A. So X minus U has to be in the null space, which is where this comes from. Okay? So in particular, if the null space has the basis, if null space of A is span of some basis V1 through Vk, then you can write every solution as uniquely as, so every solution equals U plus T1 V1 plus up to Tk Vk, where these T's are real numbers. So real numbers. Okay, this is just formalizing the idea from the previous bullet. Since you can get any solution here by adding a vector in the null space, this is just taking some explicit vector in the null space and adding it to our previous solution. Okay, so let's do an explicit example of this. So here I want to find all solutions to this matrix equation. So find all solutions. Okay, so the way that we do this is, using augmented matrices and Gaussian elimination the way we usually do. So we have 1, 2, minus 3, 1, 0, minus 1, minus 1. Okay, and we're at this point, let's only find one solution, okay, because we want to start with our u. So this, to get this simplified, we just add minus row 1 to row 2. Okay, and this gives us 1, 2, minus 3, 2, 0, minus 2. Okay, minus 3 is 3, minus 1 is 2, and minus 2 plus minus 1 is minus 3. Okay, and then we can multiply this by minus a half, R2, and we get 1, 2, minus 3, 2, 0, 1, minus 1, and 3/2. Okay. So, and then we can, in order to get this into reduced row echelon form, we can add minus 2 row 2 to row 1. And I'll get 1, 0, minus 1. And so minus 2 times this is minus 3, plus 2 is minus 1. 0, 1, minus 1, 3/2. Okay, so here we have our pivots. Pivots in pink. And here we have our free variable. Okay, and so let's find a solution. We know that we can set the x3 freely, so let's set it to equal to 1. So we have x1 minus x3, which is 1, so we'll just write 1. x1 minus 1 equals minus 1, and x2 minus 1 equals 3/2. So this gives us u equals 1 in the x3 coordinate, and then 0 for the x1 coordinate, and the x2 coordinate will be 5/2. Okay? And that is a solution to this equation, but we want to find all solutions. Okay? So we're going to take elements in the null space and add it. So let me add a page here. So what is the null space of this matrix? Okay, so we know that the reduced row echelon form of the matrix was this. So it's this matrix. And this will have the same null space as the original matrix. So we can take the null space to be, so null space equals the span of taking the third coordinate to be 1, that's our free variable. Then the first coordinate has to be 1, and the second coordinate has to be 1. Okay, so that vector spans our null space. So the set of all solutions will be of the form u. Sorry, I should say this is the span of this vector. So all solutions to this equation, this matrix equation, will be of the form 0, 5/2, 1 plus t times this vector. 0, 5/2, 1 plus t times 1, 1, 1 for t real. Okay, and you can also write this as t 5/2 plus t and 1 plus t, okay, for t real. Okay, and that would give you the full set of solutions of this matrix by using what we know about the null space. the full set of solutions for this matrix equation. Okay, so we mentioned this in passing, but one thing I want to make clear, so the process of row reduction does not change the row space or the null space. That's why we've been doing a lot of row reduction as we find bases for the row space and the null space. On the other hand, it does change the column space. Okay, so this is something that's really important to be aware of. So be careful. Okay. So how can we find a basis for the row space or the column space? Well, again, row reduction doesn't affect the row space. So for the row space, just do row reduction to row echelon form. And the vectors that you get in the row echelon form are a basis for the row space. Okay, so the non-zero vectors, I should say, these give a basis for the row space. Okay, as for the column space, row reduction does change the column space, but so once the matrix is in row echelon form, after doing row reduction, mark the columns with leading ones. Okay, so the columns with leading ones. And unless you're in reduced row echelon form, this will just, you'll have some numbers up to a 1 and then zeros below. Mark columns with leading ones. The same columns, but in the original matrix, will be a basis for the column space. For the column space. Apologies for the small font. Okay. So let's do an explicit example of this. We have a matrix here, and we want to get a basis for the row space and for the column space. Okay, so for both of these, we're going to do row reduction to row echelon form. So we have 1, 2, 0, 4, 1, 0, minus 1, 3, minus 1, 1, 5, 1. And our first step is to clear that first column, minus row 1 plus row 2, positive row 1 plus row 3. And we get 1, 2, 0, 4, 0, minus 2, minus 1, minus 1. And 0, 3, 5, 5. Okay, so far so good. Get this a bit to the side. Okay, so next up we want to get the second row to have a leading 1, so we multiply by minus a half, and we obtain 1, 2, 0, 4, 0, 1, positive a half, positive a half, 0, 3, 5, 5. Okay, so we're just going for row echelon form, so we don't need to worry about reducing above. So let's add minus 3 times row 2 to row 3, and we get, so 1, 2, 0, 4, 0, 1, half, a half, and 0, 0. Okay, 5 minus 3 halves is 10 halves minus 3 halves, or 7 halves. And same idea, 10, this is also 7 halves. And to give this a leading one, we can make this, we can just multiply by 2 sevenths. 2 sevenths times row 3 gives us 1, 2, 0, 4, 0, 1, 1 half, 1 half, 0, 0, 1, 1. Okay, so for the basis of the row space, you just have to take the non-zero rows, which is all of the rows. So we can get 1, 2, 0, 4, 0, 1, 1 half, 1 half. If you want, you could scale that to get rid of the fractions, but that's not necessary. It would be 0, 2, 1, 1 in that case. And 0, 0, 1, 1. This is a basis for our row space. It's three-dimensional. As for a column space, so we look at the columns corresponding to the leading ones in each row. So these three columns will give us the basis for the column space. But we have to be careful. We're not taking these specific vectors. We're taking the original vectors in the original matrix. So let's get that. So the basis for column space will be the first, second, and third columns, which are 1, 1, minus 1, 2, 0, 1, and 0, minus 1, 5. OK. You could do row reduction. You could manipulate these vectors if you want basis with if you want basis vectors with certain properties, but this is a legitimate basis, and you can tell because it comes from the columns that had the leading ones. OK? Great. OK, so something that we'll notice from the last computations is that the basis for row space was the non-zero rows, which is basically so it had size equal to the number of leading ones. But the leading ones also indexed the column vectors, which were a basis for the column space. Size of basis of column space. OK, what that tells us is that the row space and the column space of a matrix, and this is, well, we can write this as a theorem. The row space and column space of a matrix have the same dimension. Okay, because as you'll recall, dimension is just the size of the basis. And this tells us that, so we can give this new number a name. All right, so it's the dimension of row space and column space. This is called the rank of the matrix. Rank of the matrix. OK. So we've talked about the dimension of the column space and the row space, but there's one other space that we didn't reference in terms of its dimension, and that's the null space. So the dimension of the null space is the dimension of the null space is called the nullity of the matrix. Okay. So let's compute this in an example. So this is the same matrix, I believe, as we, oh no, slightly different. So let's just compute this directly. So we want to compute the rank and nullity of this matrix. So it's enough to find the dimension of the row space and the null space, right? Because the column space will have the same dimension as the null space. As the column space will have the same dimension as the row space. So let's do rank first. Dim row space. So we're going to do a row reduction to get a basis for the row space. So we'll start by taking minus row 1 plus row 2. And we'll find we get 1, 2, 3, 0, 0, minus 2, minus 4, minus 2. I think we did have this matrix before, but no worries. 0, 1, 0, 1. And we're going to multiply this by minus a half. 1, 2, 3, 0, 0, 1, 2, 1, 0, 1, 0, 1. And then we can subtract row 2 from row 3 and obtain 1, 2, 3, 0, 0, 1, 2, 1, 0, 0, minus 2, 0. OK. And next up, we have, we can multiply this by minus a half to get it in row echelon form. Minus 1/2 times row 3. We get 1, 2, 3, 0, 0, 1, 2, 1, 0, 0, 1, 0. OK, so counting the leading ones, so 3 leading ones means rank 3. OK, that's the dimension of the row space and the column space. OK. How about the nullity? So let's grab this row echelon form. OK, we said previously that the null space of a matrix is not affected by row reduction. So the null space of this matrix should be determined, should be the same as the null space of the original matrix. So which vectors does this send to 0? Well, we have to use the free variable, which is this guy. This is our free variable. So if we set that to 1, what we would get is, that means that from the third row, that equation tells us that x3 will be 0. From the second row, we'll see that x2 will be minus 1. And from the first row, we'll see that, well, if it's x1 minus 2x2, sorry, if we've set x2, x3, and x4 to minus 1, 0, and 1, what we're left with is x1 minus 1 equals 0. And so that will be 1. OK, so this spans the null space. This spans the null space because the only vector where we had, the only coordinate where we had a choice was the free variable. OK, so the nullity equals 1. So in general, the number of pivot variables we just demarcate here. The number of pivot variables is equal to the rank of the matrix. And the number of free variables is equal to the nullity of the matrix. OK. And that leads us to the following fascinating results, which we're going to use a lot. It's dimension theorem for matrices. This is also called the rank-nullity theorem. OK, if A is a matrix with n columns, then the rank of the matrix plus the nullity of the matrix is equal to the number of columns in the matrix. Okay, and this makes perfect sense because this is the number of pivot variables, each of which occupies a column, and this is the number of free variables, which are the other columns in the matrix, right? So this makes perfect sense. Okay, so now we've got a sense for row space, column space, and null space. So the row space of A is an important matrix space, as is the column space of A and the null space of A. But there's another natural set of things to consider, which are the row space of the transpose of A, the column space of the transpose of A, and the null space of the transpose of A. Okay, and something that takes very little logical steps to see is that the row space of A is the same as the column space of A transpose. And the column space of A is the same as the row space of A transpose. These are equal. On the other hand, this is not equal. The null space of A is not the same as the null space of A transpose. Okay, so that means we have 4 fundamental matrix spaces. So we have the row space of A, which is the same as the column space of A transpose, the column space of A, which is the same as the row space of A transpose, the null space of A, and the null space of A transpose. These are called the fundamental matrix spaces. Okay. To give you a bit of a geometric picture for what these spaces are like, I'm going to define orthogonal and orthogonal complement. So we say that vectors are orthogonal, and we want them to be in the same space. So let's say vectors v1 and v2 in Rn are orthogonal if their dot product is 0. Okay, and you'll remember dot product from when we described matrix multiplication. So that's the definition of orthogonal. The orthogonal complement is the set of all vectors. So if W is a subspace, so let W be a subspace of Rn, then we define W perp. You can read this as W perp, or the orthogonal complement of W. This is the set of all vectors orthogonal to every vector of W. Okay. So the geometric picture So orthogonal means more or less that they meet at a right angle. Okay. As for orthogonal complement, so let's say we're living in R3. If we have W, which corresponds to a certain line, so let's say this is W, a line through the origin, then W perp will be the set of all vectors that are orthogonal to that. So it'll be a two-dimensional plane that the line W passes through perpendicularly. So this is W perp. Okay. So these four fundamental matrix spaces are orthogonal complements to one another. So the row space of a matrix A is equal to the orthogonal complement of the null space. And the column space, and this is in Rn. Okay, so if A is, maybe I should say this explicitly. So let A be an m by n matrix, then the row space and the null space are orthogonal complements in Rn, whereas the column space of A is the orthogonal complement of the null space of A transpose. And that's in Rm, which is the output space of A as a function. OK. And this last slide, I really just think it's important to review the Theorem 4.88 in the book. This goes through a lot of statements that are essentially equivalent to a matrix being invertible. And many cheerful facts is a reference to Pirates of Penzance, for those of you who don't know. So a matrix being invertible is the same thing as saying that it has full rank, or meaning its rank is equal to n, or its nullity is 0, meaning there are no vectors that are not 0 which map to 0. Okay, and there's all of these different things in terms of our fundamental matrix spaces that we can say that are equivalent to invertibility. But really, what this table does for us, what this list does for us, is reinforce to us how many equivalent, how much linear algebra is kind of a unified topic. Like columns rank is equal to row rank, and the null space and the rank are related in this fundamental way. Everything is kind of interconnected, and the key is invertibility. So with that, I'll leave the lecture there, and thank you for your attention.